Hi, I'm Jackie Garofano, Chief Technology Officer at CCAT, the Connecticut Center for Advanced Technology. Our team is bringing to you a series of videos all about model-based definition. Here we have a lineup of many technology providers to show you how to do automated welding using MBD.
Hi, I'm Nasir Mannan. I'm the Principal Engineer here at the Connecticut Center for Advanced Technology. Today, we're going to be going through showing you the real power of the digital thread. Now, what I mean by that is how we can reuse design data that's given to us in a digital format across various pieces of software to get to the end goal. In this particular case, we're going to be showing you how to generate a robotic welding program using model-based definition. We're going to go ahead and open up the Smith bracket design in Siemens NX. So here I have the modeling workspace loaded up, and I've got the Smith towing bracket loaded up as well in this workspace. I'm going to double click on the back view of this particular design. And for reference, the base plate is 2 feet by 2 feet. This particular bracket is used primarily in the naval maritime industry. You can see that it has a number of different welds associated with the part design. We've got intermittent welds, we have all-around welds, and if we go ahead and view the reference sets in this model, I'll go ahead and hide the main body. You can see that there's one main body that contains the base plate and the individual plates that are welded to that main base plate. But the majority of the bodies are individual welds that are actually modeled in the design. And so if we take a look now at the weld callouts, I'll go ahead and double click on the weld callouts. And you can see now that the weld callouts are associated with specific bodies, the specific weld bodies. So this particular weld callout is saying that this is a fillet weld that is 8 millimeters in length, and it's an intermittent weld where each one of the weld segments is 50 millimeters long, and then there's 70 millimeters between the start of the intermittent welds. In other words, from this surface to this surface is 70 millimeters. In this particular case, this particular weld is showing an all-around weld, 10 millimeter fillet weld. And similarly for the other welds, you can see that this is also an 8 millimeter fillet weld, 50 millimeters in length, and the distance between the start points of 2 consecutive welds is 100 millimeters. If I double click on the weld callout, you can see here that the selected objects that are associated with this callout, in other words, this particular callout is assigned to 15 different faces, and those are the 15 faces that make up these 3 individual weld segments. I'll go ahead and show the main body again. Since this is a Siemens NX native file, what I want to be able to do is encode this file in a QIF. So I will activate Capvidia's MBD Connect for NX application. That is a plugin inside of Siemens NX. If I click on the application tab and go over to MBD Connect for NX and activate it, I now have a tab on my ribbon bar for MBD Connect. I can click on that, and now I have an option to export QIF. So I can go ahead and export this file as a QIF. And what that particular function does is it grabs all of the views associated with that model, in other words, the back, bottom, front, and the other views that you see in the tree here, as well as the CAD definition and the weld callout, and encodes that in the QIF format. I'm now in a position to open this file in MBD Vidia. In MBD Vidia, what I can do is go ahead and open that particular file. And on import, what MBD Vidia does is it actually automatically generates a weld inspection report. So what we can see here is the CAD design, and if we activate or view the annotations, you can see that all of the weld callouts were successfully imported, as well as generating the weld inspection report. Each weld callout has a balloon number associated with it. So if I hover my mouse over one of the identifier numbers, number 5 here, you can see that it highlights the associated welds on the model. We can take a look at the weld inspection report by navigating down to the bottom panel and selecting the welds tab. And you can see here that we have tag 1 through 6 that we can see on the screen here, and all the weld definition associated with those 6 weld callouts. With that, all I have to do is go ahead and save that file again. And I'm now in a position to open this file in Visual Components. Visual Components is a software that allows you to do full factory simulation. In this case, we're going to be doing offline robot programming, another capability within Visual Components. And we've modeled here a robotic welding work cell. We have a 6-axis FANUC robot as well as a 2-axis FANUC positioner. And the welding technology that we're using is Fronius. Fronius has 2 key technologies that ensure perfect welds. One is seam tracking, and the other one is wire sense technology. With those 2 technologies, we can nearly guarantee that we get perfect welds every time. In our particular case, since we have this Smith bracket that has 2 eye plates on it and the additional support bracket, we're going to create a separate program for the eye brackets, pre-weld the washer plates on them, and then we're going to weld all 3 of the plates to the main base plate. So we'll go ahead and open up the CAD design, and then we'll go ahead and load the QIF weld information that's contained within that QIF file. In Visual Components, I have set up our virtual robotic welding cell. So in this case, we're going to go ahead and import our CAD geometry of just the eye plate. So we'll go over to our import component. We can select our eye plate step model. And the imported CAD geometry is imported with the original CAD coordinate system. So we'll go ahead and position this so that we're on our rotary plate. So we'll select the move command, and we can position this roughly above our positioner. Now, using the align command, we can place this down on the rotary surface. With that, you can see that as we imported the step file, in this case we saved it out as a step 242, so you do see the weld callout associated with the weld. We don't need that in this particular case because we will be importing the QIF definition. So we can go over to the modeling tab. This is not necessary, but we can delete the markup for clarity. Now we just have the CAD geometry. And in order to import the weld definition and for Visual Components to automatically generate the weld program, we're going to go over to the Program tab, select the robot that we want to program, and then select our part onto which the weld information will be imported using the QIF importer. From here, we'll go to our templates, import QIF welds, and we will select our iPlate1 QIF file and click Open. On import, Visual Components automatically generates the weld program. So if we zoom in, we can actually see the robot positions that the particular simulated cell needs to go through in order to accomplish the welds. You can also see the points, the safe positions that the robot goes up to between the welds. Now that the weld program has been generated, we can go ahead and simulate that weld program. So in Visual Components, I'm simply going to click on the play button. We'll slow this down for now. And we can see the touch-off points to indicate the start and end of the weld for the particular segment. For the rest of this program, we can increase the simulation speed so that we can see the entire simulation done faster. With that, we've completed all the welds. Again, being able to visualize the actual welds in the simulated environment highlighted in red. If any collisions were to take place, we can adjust the orientation of the robot. We can adjust the approach angle. Next, now that the programming is complete for welding the washer plates onto the eye plates, we can generate the program to weld the main plates onto the base plate of the Smith bracket. In Visual Components, I'm going to go ahead and go over to my import geometry function. And I will open up my step file. The CAD geometry will be placed in the environment according to the coordinate system that was saved out in the CAD. In this particular case, I'm going to rotate and position the CAD file onto my positioner table. So I can go ahead and click on the move function, and I'll go ahead and rotate this 90 degrees. We'll bring it up and over to the positioner table. And at this point, I have it roughly positioned where I want it. I can go ahead and use the align function and select my two surfaces that I want aligned. So now my part is sitting on my table. You can see that by opening up the step file. In this case, we saved it out as a step 242 file. I can also see my model-based definition, the weld callouts. In this particular case, these weld callouts I'm not going to use, so I'm going to delete them. And I'm going to import the weld information from the QIF to generate the robot program. So if I go over to the Modeling tab, I'm going to highlight and just delete for the sake of having a little bit of a cleaner view. And in this case, I want to be in the Program tab, select my robot, so that becomes my active robot that I'll be programming. And instead of going through and manually clicking on the CAD model, defining where the weld starts, where the weld ends, and putting in my weld information, and then setting up my axis orientations, I will just go ahead and import the QIF, and you'll see the weld program automatically generate. I have to select my workpiece first, then I'll go over to Templates, import QIF welds, and I can import the QIF file. And on import, you can see on the left, my program is automatically being generated, and we'll go ahead and quickly take a look at the generated program. If I zoom in, you can actually see the path that the robot has to take in order to accomplish the welds. Now that we have the robot program generated by visual components, we'll go ahead and run the simulation. We'll see here that there's going to be 2 touch-off points to identify the start location of the weld, and 2 touch-off points to identify the end of the weld. This is part of the Fronius subroutine, and you'll see here in the simulation that we're actually simulating and we can visualize the welds as they're being performed by the robotic system. For the rest of this program, we can increase the simulation speed so that we can see the entire simulation. And that's it. The robot program simulation is complete. We can go ahead and visualize all of the welds that you see there in red. We also have the ability to visualize any collisions that would have happened during that program. In this particular case, there was no collisions, so we can go ahead and post out this program for the actual robotic work cell. Throughout this process, you saw 3 different technologies being used. One, the main CAD, which is Siemens NX. You saw Capvidia solution using MBD Connect for NX as well as MBD Vidia. And then you saw visual components to generate the actual offline robot program for welding. The ability to reuse this QIF format across multiple different software solutions is really the power of the digital thread and about reusing digital information across various different aspects of producing a part. The next step is to post out the program and actually send it over to Fronius in Indiana, where they'll perform the actual weld on the physical work cell. At Fronius, they're going to be loading that program onto their robotic welding work cell and executing that program. The main base plate will be fixtured down onto the rotary tabletop. As you saw in the simulation, the part is rotated to several different positions so that the welding nozzle can reach those areas to perform the weld. Fronius will be using their perfect welding technology. There's 2 technologies involved in this. The wire sense, which is a technology that enables the wire to understand where the actual surface is. They pulse the wire back and forth out of the nozzle in order to touch off on the part. And this gives the system the ability to know exactly where that start point is. And then they move forward to the end point. They use the wire sense technology to probe or touch off on the part so they can extract the exact endpoint. The idea here being that the robot program that was generated off of a CAD model, which is in a perfect condition. In other words, the seam is going to be a perfectly straight line. But in reality, there's always going to be some discrepancies or distortions. This technology has the ability to compensate. The other technology is called seam tracking, and seam tracking allows the welding technology to understand if the seam is actually deviating from that straight line. So we have the start and end point, and if the seam is supposed to be straight, whereas in reality there's a slight curvature to it, the seam tracking technology can place the welding head exactly where it needs to go. Both of these technologies, the wire sense and seam tracking, are used throughout. The part has been welded at Fronius headquarters in Indiana and has now been shipped back to us here in East Hartford, Connecticut at CCAT. We have the part set up here on the rotary table, ready for the inspection process. We're going to show you how easy it is to set up that process in Polyworks Inspector software to be able to measure the leg length and the length of the welds using model-based definition. We've opened up a new Polyworks Inspector project, and we're going to import the CAD model. So we're going to click on the import icon, import CAD models, and we're going to select the Smith towing bracket. In this case, it's a QIF file. This is a neutral model-based definition format. We can actually see the imported CAD model with all of the welds highlighted, the welds faces highlighted in blue, and all the inspection for those welds imported from the QIF file. So here we have a number of inspections on the widths of the welds, the length of the welds, and if we go back to our tree, you can see the number of faces that we have associated with the welds. At this point, we're all set with setting up the inspection project. Now it's time to take the scan of the part. We're going to go over to M3DI AO software. We're going to be using a M3DI VeriScan Flex scanner. The scanning technology is set up on a 6-axis collaborative robot, and the part is sitting here on a 1-axis rotary table. So in total, we have 7 axes of manipulation on this part to be able to get to all the different surfaces we have to see to grab the information to be able to inspect the part. In the AO software, we're going to go over to the automation tab, and we're going to open our program to scan this part. I've got the program saved as Smith bracket, and if we open it, we can take a quick look as to what's going to happen. We're going to take a series of scans on the part. The robot will move positions. We'll take another series of scans, and the robot will move to its last position and take another series of scans until moving back to home position. The robot currently is set up so that we can make sure that we have enough coverage on the part. So on starting the program, we're going to move the robot first to the home position and then execute that program. The robot will move first to its first vantage point position, and it's going to start projecting a fringe pattern on the part. A fringe pattern is a known black and white stripe pattern, and that stripe pattern gets deformed as it hits the surface of the part. The camera receives that distorted pattern, and from that signal change, it's able to calculate the 3D surface information from the vantage point that it's seeing on that part. Because it's line of sight, the part surfaces have to be presented to the scanning technology so that it can capture more information on the areas that it didn't see in the previous set of scans. And so the robot has moved to another position in order to get some of the information on the underside of these holes. The robot's moved the scanner now to a position where the camera has that vantage point. While this is happening, we can see in the software, AOS, the scans coming in. The scans come in aligned because the position of the robot and the rotary are known. And once all of the scans have been taken, the scanning software then merges or combines all of the scans together so that you have a single STL or mesh file that we can then export out to the inspection software. Now that we're done with the scan, we can import that into Polyworks Inspector and run the weld inspection process. Since the scanning is done, all we have to do is import polygonal models, and we can choose the scan that we just completed now. The import of the scan is going to come in not aligned to the CAD model. So the first thing we're going to want to do is an alignment. So if we drop down, we'll choose the best fit. We'll apply that. And now we can go ahead and right click on all of the weld faces and perform the weld measurement. So here, Polyworks Inspector is automatically extracting all of the weld measurements that are required to be taken, and we'll take a look at the measurement results once it's finished. So at this point, it's finished extracting all the measurements. If we go into the control viewer, we can see that all the welds have passed inspection. We have a number of different inspection criteria, such as the width of the weld, the length of the welds. And we can now export this out in any type of inspection report format that we desire. You can see how with just a few mouse clicks, we can go from design all the way to fully executed inspection with an output inspection report using model-based definition. I'm Nasir Mannan. Thanks for watching.
Thanks to all of our tech partners who contributed to this video. As you can see, the digital thread has made its way from Connecticut to the Midwest. And so it's really important for us to be able to automate processes and keep that digital thread connected. That's all about the power of model-based definition. Thanks for tuning in.